Okay, so welcome to graph theory. In this video, we'll be talking about, well, a few applications of graph theory. We won't do anything like super serious in this video. I do want to start off by saying, though, that these graphs that we'll be talking about in this chapter are not the graphs that you probably remember in calculus, where something like this is called the graph of a function, right? All the points x comma y that satisfy the function formula. So that's not what we're gonna call graphs in this chapter. A graph for us is going to be defined as a pair of sets. Usually we call it G for graph, but we can call it H. We really can call it by any name, but we usually use a capital letter to describe graphs, or to name graphs. V and E are the two defining sets of a graph, and V is a finite set of things that are called the vertices of the graph. The singular form there is vertex. And E is a collection of unordered pairs of elements in V. Right? So unordered pair, that's important here. In fact, there is a type of graph where you take ordered pairs of elements in V. Right? But for us, let's define the unordered version to be our graph. And they're called edges. So let's visualize what this means, right? This is slightly abstract here using the definition. Let's say I define the graph G to be the set V for vertices containing, letters A, B, C, D, and E. And capital E is a collection of unordered pairs, right? So I can have the unordered pair AB, and it's unordered, so you can use curly brackets to denote them if you want. BC, let's say BD, and then DE. So that's a graph. And what we can do with graphs, and what actually gives it a lot of the power, right, of using graphs in solution or in problem solutions, is you can visualize graphs as follows, right? You can draw each vertex as a point on your paper and basically connect two vertices by a line if that pair is an unordered pair in this set E, right? In other words, if it's an edge. So we see that A comma B is an edge. So AB, BC, BD, and DE. Right? And so this is the graph G here that we just drew. In fact, I don't really like seeing these nested curly brackets, so I'm just going to use like parentheses for all of them. I think that looks much better. But they're unordered pairs. Right, so I could write B comma A and it denotes the same edge. Right, so these are your edges, these are your vertices. And where graph theory is really helpful is when you have to model, maybe a system or a real world phenomenon, right? Where you have things, your vertices, which are related in some way, your edges, right? And so we'll give a few examples of that in this video. Let's look at this one, where it's not exactly obvious at first that you can describe this using a graph. Right, so the question is, you have a floor plan here of a building, and can you walk through each wall of the building below such that you start and end in the same room? Right, so you assume that you're somewhere here. Say you're starting out here in the upper right corner. And each of these walls, let's count them as separate walls, right? So the question is, can you trace a path such that you visit each room. Well, such that you hit each wall, I should say, and go back to where you started. Right, so for instance, if I had done this, now I'm back to where I started. Right, that's a path through the rooms of the house, through these walls. Now I don't use all the walls in these paths, right? So let's try again. Maybe I use this wall here, and then I use these. Oh, then I can use these. Right, so in this room in the bottom right, I've used all of them. And I encourage you to try it yourselves at home as well. If you're watching this, can you trace a path such that you're visiting all the rooms in this building? Okay, so now I'm back to where I started, right? And I see here that there are some walls here that I haven't actually used. And so how can you actually decide this, right? How can you actually tell whether or not it's possible? Well, modeling this scenario as a graph is actually going to help us here. And what I'm going to do is, I'm going to say, denote each room using a vertex. Okay. And connect two vertices if there's a wall in between those rooms. And in fact, we're going to do it for every wall in between the two rooms. Okay, what does that mean? Say I label all the rooms here. Right, so this is room 1, this is 2, this is 3, this is 4, and this is 5. And the outside is one big room, call it room 6. So as a graph, what's that going to look like? So 6 is connected to, well, all the rooms through a lot of these walls. So 1, 2. So 1 is connected to 2 once, using this wall over here. 1 is connected to 3 using this wall, and connected to 4 using this wall. 2 is connected to 4 using this wall. 2 is connected to 5, and then 3 to 4 and 4 to 5 are connected. And what else? So 1 is not connected to 5, 2 is not connected to 3, right? So all we have left are the outer walls that connect everything to 6. So let's do this. I'm gonna put 6 up here, and it's connected to 1 actually twice, because there are 2 walls there. It's connected to 2 twice as well, and then same for 3 and 5. And then 1 last connecting edge from 6 to 4 for this edge. Okay, so you may be thinking, well, doesn't this look more complicated than what we started with? Now I can't even see the building, right? It's just some points that are connected to one another. But now think about this path that we just drew. Right? You started at room 2, right, or in room 2. And from room 2, you went to 6, right? So I can actually trace the path here by drawing along the edges in my graph, corresponding to which wall you're passing through. So this was, let's say, from 2 to 6, going here. So I use this. And then 6, you go inside to 5. And then from 5, you go back to 2. Then from 2, now you're here, you're at 4. From 4, you're back to 5. From 5, you go out again, now you're back at 6. and so on, right? 6 to 4. Should have used a shorter path here, but I'll just finish this. 4 to 3, 3 to 6, and then back to 3. So we're just erasing the edge and drawing in the blue one if we're using it. And then from 3 to 1, from 1 to 6, and then 6 to 2. Okay, and now you're back to where you started here. So the 3 walls that we didn't use, which is this wall, and this wall, correspond exactly to the edges here that remain red. Right, so it's this from 1 to 6 we didn't use, this one from 1 to 4, and this one from 1 to 2. Oops. And so our question here of can you walk through each wall of the building such that you start and end in the same room? We can now rephrase that question as can you walk along all the edges of the graph on the right? Well, let's call it like G. So off the graph G, exactly once, and return to where you started. Right, return to the starting vertex. And so what we've done here is we had a situation here in the real world. I mean, as real as you can get, walking through walls. But we were able to just get what we needed from the problem, right? What was important in the problem? Well, what walls you were walking through and how the walls relate to the rooms, right? So all of that information is encapsulated in the graph I have on the right. And so solving that problem in the floor plan is equivalent to solving this problem on the graph. And in this case, we'll actually see an easy way to solve this problem on any graph, not just a specific graph. And you'll find that the answer here is actually no. It is not possible. All right, so this room, nope. Even if you could walk through walls, you can't walk through each wall exactly once and come back to where you started. And, well, I'm going to end with a few more examples here, just to give you a taste of the other applications of graph theory. For instance, maps, right? When you ask your application, right? So in this case, it's Google Maps, but whatever maps you used. What's the fastest way to get from point A to point B? That's a graph theory problem, right? In a sense, you can actually view these intersections as vertices. And these roads as edges. And so the maps that you can see on your phone, right, or on your computer, they're just actually like huge graphs. And each edge here is going to be associated with some number that tells you how long it takes, in this case, to walk along that road. So if it takes 10 minutes here, maybe 15 minutes here, and then maybe 7 minutes to the end here. But here and the other way, it's like 8 minutes here, 5 minutes here, like whatever, right? There are numbers assigned to each edge, depending on how long it takes for you to walk that edge. And so now the question is, what is the fastest path through the graph, starting at this vertex, ending at this vertex, right? Going from UTM here to Popeyes. That's a graph theory problem. Also, maybe you want to visit all the vertices in a graph, right? say you were on campus at UTM and you wanted to find the fastest way to visit each building exactly once and return to the building where you started. Right? So that's also going to be a graph theory problem, which you can describe by putting your buildings as vertices and the distance between them as edges with associated weights. Right? And so for this particular graph here, I could be going A, B, C, D, E, F back to A, and that will give me a total of, I don't know, 37, right? When you add all of those numbers up. But I could also go A, D, B, E. Let's see, can I do that? No, I can't do that. A, D, B, F. No, I needed to go from A, D, C, B, E, F, A. There. And that's going to give you a tour with a different total, right? So this is like 31, right? So that's a shorter path or shorter tour through all the vertices. All right, so that's actually a graph theory problem that's quite famous. It's called the traveling salesman problem. Right? Because imagine that you're a traveling salesman. Or I guess now it's usually called a traveling salesperson problem. And you want to find the most efficient way to visit all these cities that you want to sell stuff in. Right? So it's pretty easy to think of applications here. If you're a driver delivering packages, right, for the post office, can you find the best or the fastest way to visit all the houses on your route? Right? So everything we talked about here, these are just examples of applications of graph theory. And hopefully that gives you an idea of some of the problems that you will be able to solve after we look at this section. Right? And again, the power lies in this abstraction where you're given something in the real world and you're able to translate it into the language of graphs so that you can solve the problem in the world of graphs and then translate that solution back to a real world solution to your problem.